Welcome to another stream of CosmoQuest Astro 101. I'm your host, Dr. Matthew Richardson, and we're gonna definitely have some fun today, hopefully. Well, I'm gonna have some fun. I always have fun. I hope you guys have fun along with me. Alright. So let's make sure that everyone can first hear and see me just fine. Let me make sure that that's going well. Yes, I can see myself on Twitch. Alright. So guys, today's plan is to kind of somewhat pick up our discussion where we exactly the ghostly weird particles. We're going to pick up our discussion where we left off last time, kind of, sort of. So in our last stream, we did a calculation for the rest mass of neutrinos, and the reason why we did it was because of the fact that they could possibly play a major role in determining whether or not our universe is open, closed, or flat. And of course, with those particular geometries for our universe, we can get different possible fates. For example, the Big Crunch, or basically expansion forever, the heat death and stuff like that, the Big Freeze. And that topic really was very interesting to me. So I was thinking about, well, what are other ways in which the neutrino's rest mass can be calculated? Because at the current moment, for the calculation that I did, we know that the neutrino rest mass, or at least from laboratory experiments, that it isn't nearly as high as high as the calculation I did in the last stream. Hey Guido, and so I'm kind of back at this particular topic, that is calculating the neutrino rest mass, but by another means. And of course, because this is astronomy, we want to be able to see how we can use astronomical observations to get at this particular value for the neutrino rest mass. So, what was very interesting for me to find out. So I'm not going to be talking about IceCube today. I'm actually going to be talking about another detector. But yes, IceCube is an experiment that has the ability to be able to detect neutrinos. But today I'm going to focus on a different experiment that also has the ability to detect neutrinos. But one thing that I found out that was very interesting was the fact that at the current moment, today, there's only actually 3 known sources for neutrinos. Now, hopefully the information where I got this information from is correct, but these 3 known sources would be the sun. Well, an image of it pictured here on the screen. Then there's also this blazar being an active AGN, or an active galaxy that's hundreds of millions of parsecs away from us. And then lastly was this supernova 1987A, that's located within the Large Magellanic Cloud. And so I'm going to quickly go to that. We're going to spend a little bit of time talking about this supernova, and then we're going to eventually move on to the calculation that I did for the neutrino rest mass and the observations related to this supernova. I kind of got a late start today, so I have to quickly find this amongst all of the pages I have open here. Not web pages, but pages I've opened on my laptop. Where are you? You are here, Keynote. Here we go. All right, so supernova 1987A. This supernova went off sometime, I believe I read it was in February of 1987. The supernova is located in the Large Magellanic Cloud. And one of the interesting things I found out about this particular supernova was that for the observations of the supernova, the neutrinos somehow were able to reach us before the light, which was kind of weird. I'm hoping I read that correctly. And I think the explanation for that was that neutrinos themselves they don't really interact that much with matter, and they were able to pretty much just freely move through the supernova towards us. However, there was a lag in the light coming from the supernova to us due to the fact it had to go through the matter associated with the supernova. Now, I'm hoping that that's correct, because to me that doesn't make much sense, because of course light is the fastest moving thing. that we know in the universe, and neutrinos, of course, are extremely fast as well. But because of the fact they have mass, they should move slower. But the key thing that we want to talk about here is or are the neutrinos or the neutrino observations from this supernova. And so the neutrinos were discovered, well, they're actually detected by multiple experiments, but the experiment that we're going to be focusing on today is the neutrino detector that's located in Japan called the and I hope I get this right, Kamiyo Kande or Kande or whoever's good with being able to pronounce these words. By all means, if you want, put the correct phonetic spelling for it in the chat. But what I was able to find out about this particular neutrino detector is that it's located in Japan, and it's actually located underground, like most neutrino experiments. It's located underground in a mine that's roughly about 1 kilometer underground. Now, the actual detector itself is essentially this room that we're looking at here. It's cylindrical in shape, and within the room we have a bunch of pure water. And surrounding the pure water, we can kind of see also are these photomultiplier tubes, which will detect light that's being produced by the neutrinos. Let me go a little bit more into that actually. So neutrinos themselves are, for the most part, they don't really interact with other matter. But they do interact, though. That's the key thing about it. They do interact. And when they interact, they can produce charged particles. Now, in the case of this detector, what's occurring is the neutrinos, of course, are coming from some source, in this case the supernova 1987A, passing through Earth, eventually getting to within this chamber here, going into the water, and while within the water, they're interacting with other particles to produce charged particles, or atoms to produce charged particles. I think I said that right. And these charged particles are, while within the water, are moving faster than the speed of light. Well, let me be careful with that. They're moving faster than, I believe it's the not the group, but the phase velocity of light in water. And due to the fact that these charged particles are moving faster than the phase velocity of light within the water, they end up producing light. And this particular light that they're producing is known as Cherenkov radiation. It's pretty much the same type of light that's going to be produced within fluids that are around like same light that's produced with what is it I'm looking to say here? Like with the Large Hadron Collider. But basically, whenever you have a charged particle within a medium, and that charged particle's velocity travels faster than the phase velocity of light within that medium, you will produce this particular type of light, which is what is occurring within this neutrino detector. You can kind of get a sense of how big the detector is by, if you look closely within the image, there appears to be like 2 people on a boat, and they're kind of like just paddling through the water within the detector. So this is a pretty huge, a pretty big, large chamber, is serving as a means to detect these neutrinos. And so, of course, I stated earlier that this detector was able to detect neutrinos from supernova 1987A, and the plot that was produced from this detection is shown here, where along the y-axis we have the total energy of the neutrino as a function of time. So basically, at some point in time, I mean, they've given some sort of relative time here, starting at -60, which is -60, basically 60 seconds before the actual detection of the neutrinos from the supernova. Basically, we're getting background radiation, particle radiation, neutrino particle radiation over a course of 60 seconds, and eventually we get this large jump and the energy of the neutrinos. And it seems like it goes as high as almost close. It looks like it's close to like 36 MeV, and eventually the energies decay, and this whole process happens over a course of roughly about somewhere 12 to 15 seconds. It looks like with this plot. And so, what I thought would be very interesting would be to present a method of being able to determine the rest mass of neutrinos from this detection. And so before I continue, I'm going to quickly take a look at comments. So let's see. So Hanny, that sounds right. Yeah, I mean, so you're talking about the fact that the neutrinos appear to come before the light. Um, to me, that's still kind of weird, right? I kind of figured that if there were a supernova coming towards Earth, and actually able to destroy Earth, I kind of figured what would happen, and I mean, this is kind of how the events would have unfolded in my mind. The light would get to Earth first, cook Earth roughly, or at the very least, heavily destroy our ozone layer, kill it actually, and then eventually, if you don't die by the light, which you probably should, by the radiation, the photons coming and hitting Earth, the particles, both charged and neutral, like these neutrinos, will come through and kill us. Not so much neutrinos, because neutrinos pass through us every day. I mean, millions of them, and I mean, we're good for the most part. But at least, but definitely the charged particles would come through and kill us. I kind of figured the light would get here first, and then the neutrinos and charged particles. But in this situation, I'm understanding that the neutrinos got here first for this detection. And so the supernova itself should when it occurs, it should be rapid. Um, the so in this situation, supernova 1987A. I'm not too sure exactly what was the cause of the supernova. Like, for example, if it's a high mass star, at the end of its lifetime, it'll undergo a supernova type 2. Um, and then there's other types of supernova as well, like, for example, the ones related to white dwarf supernova. But generally, if I'm remembering correctly, if you're looking at the light curve for a supernova, the the amount of light coming from the supernova should rise rapidly and then decay slowly over time. So it should be a very fast process at the beginning. Thank you, Hanny. Nuclear reactors. There we go. That was what I was trying to get at. So, yes, nuclear reactors. You basically have this Cherenkov radiation being produced within nuclear reactors. Thank you. Right now, my brain is going very. It's trying to keep up. Like I said, I was just like quite literally like 30 to 45 minutes before this stream. I was trying to quickly try to prepare the content and get through the problem I was working. Um, let's see. So Noel asks, is there a process within a star that produces neutrinos before the supernova? So, as stated earlier, the sun actually produces neutrinos, um, and so there there are particle interactions occurring within the star, mainly like within the core of the star, fusion, and these processes produce, or this process, the fusion process produces neutrinos. So if you're talking about, for example, with a non-main sequence star, a red giant, I would imagine, yeah, I can imagine that there would be, if the red giant itself is actually fusing some elements within its core, during the process of fusing those elements, it could be producing neutrinos. It would be producing neutrinos. Oh, okay. I just saw your next comment. Besides the normal fusion, I suppose. Um, so how long does it take for a supernova to propagate from the core to the surface of the star? That is a good question. So as I understand it, if you're talking about well, in this case, you're talking about. So essentially, what happens initially is that the star would collapse on itself, and then the actual explosion is the supernova. And exactly how long that process takes, I think it's extremely fast. To give an exact time to it, I can't say at the moment. All right, and so my thoughts were for today were to go ahead and take the data that we see here and see if we can do an estimate for the rest mass of a neutrino. And so that was the part that I was kind of like trying to really scramble and get together really quickly before the stream. So we're going to go ahead and we're going to switch the scene here to this one. All right. Oh, I'm showing part of the calculation I've made. Okay, you guys are seeing a bunch of like crazy numbers on crazy letters and numbers on the screen, which will be explained in a second. So I'm going to scroll back up. All right. So again, and I've named this neutrino rest mass calculation 2 because we did a neutrino rest mass calculation in our last stream, and for that calculation, we used the critical density to kind of get at the rest mass, the critical density of the universe to get at the rest mass of the neutrino. But now we're kind of using this concept of the fact that, or let me first read the problem and then I can get to that actually. So the problem is this. We know that we had the supernova go off in 1987 and that it occurred within the Large Magellanic Clouds. Now, given the fact that it's a supernova, it makes it a standard candle. And you can use that to be able to calculate a distance, in this case, to the Large Magellanic Clouds. And so I've read that, and I've gotten a few different figures for the distance, but this is kind of like within that range. So basically, this supernova occurred at a distance of roughly about 160,000 light years from Earth. Now, of course, in the plot that I just showed, there were multiple neutrinos that came from the supernova. But in this case, I've taken two neutrinos. One that I know I kind of saw somewhere within the ballpark of roughly 36 MeV, and the other one that I saw, kind of like at the lower end of the neutrinos coming from the supernova, was kind of about 9 MeV. So they're roughly off by a factor of 4 here. And these energies, now note these are total energies, and I'm going to get to why that's important in a second, but they were detected roughly within 12 seconds of each other based off of the plot. And so we're basically going to use this information to kind of estimate the neutrino rest mass. Of course, we're going to assume, though, the neutrinos that we're detecting here both are coming from the supernova and that they were emitted at the same time. It's key that we assume this this point, because if we don't assume this, the calculation isn't going to work, or I can't calculate it the way I've done it here. So Hanny asks, are they sure that both neutrinos were the same type, or is the different types pretty similar? That's a very good question, Hanny. So that's actually another assumption that we have to make for this calculation. We have to assume. Now, from my understanding, with these particular detectors, you can get at the flavor of the neutrino. But for our calculation, we're just going to assume that the neutrinos are of the same type. You guys always give great questions. All right, here we go. So right. So we know that both neutrinos are traveling at the same distance, but they have different total energies. Now, whenever you're thinking about particles, like particles like the neutrino, or even electrons, protons, neutrons. Um, Whenever you're talking about the energy of the particle, two types of energy should come into mind. The first energy being the rest mass of the energy, which is basically the energy that the particle has just for existing. Whether it's moving or not, just standing still, or as the name implies, rest mass, it being the particle being at rest, it has that energy. The other energy that it would have is its energy due to motion, or its kinetic energy. So, whenever you're talking about the total energy, it's actually composed of essentially the kinetic energy of the particle and its rest mass energy. Now, at these particular energies of 36 MeV and 9 MeV, and under the assumption, of course, that the rest mass of the neutrinos is very, very small, then for the most part, these total energies are almost wholly the kinetic energy of the particle. And so that bit of information is very important, and I'm going to come back to that particular concept in a second with this calculation. So they're both at the same distance, and they have different total energies, which is another way of saying, in this case, because we know that the total energy is roughly almost the same thing as the kinetic energy in this case. And the kinetic energy is related to the speed of the particle, or its velocity. We know that the different total energies is the same thing as saying different velocities. So at the very start, we can always say that the difference in time of detection between the two particles must be equal to the distance that they both have to travel, which is the same distance, divided by their change in velocities. And of course, upon solving for their change in velocities, we basically get the distance they traveled over the change in time. So at this moment, of course, we aren't really at the rest mass of the particles, but we need to be able to now relate the rest mass of the particles to their velocities. And so we can go ahead and use Einstein's famous formula, which is very useful with particle physics. That the energy of the particle is equal to mc squared. But in this situation, you'll see, I'll highlight this, that the equation is, and I cannot highlight this. Oh, that sucks. All right, I can't highlight this form of the PDF. But basically, we have that the energy is equal to gamma times m, the rest mass of the neutrino, times c squared. Where this gamma factor, or the Lorentz factor, or boost, depending on who you're having the conversation with, is important to be able to take into consideration how the energy of the particle changes with its speed. In the case where the particle is not moving, you simply just get the rest mass of the particle because gamma equals 1. But as the particle begins to move faster and faster and faster, its total energy, which is E in this case, increases. And basically, gamma turns out to be this whole factor that we have in the denominator for the next portion of the equation. The square root of 1 minus the ratio between V over C quantity squared. So, we can of course use this now, though, to be able to get at the velocity of the particles. So we can solve the equation for V, and now we have a very general equation for being able to say what the velocity of the particles are in terms of their energy. This next part is, and this is a trick that I learned so long ago with dealing with very complicated equations, like the one we see here for the velocity. Whenever you're dealing with an equation that has like factors of the square root of 1/2 and stuff, or powers of the square, or 1/2 powers of 1/2, you can typically it might be easier to go ahead and try to see if you can use some sort of expansion technique, like a Taylor series expansion, or in this case the binomial expansion, for being able to simplify the math. And so that's exactly what I've done here for the velocity. I primarily focused on the part that's bracketed. Use the binomial expansion for the expression I'm showing there in parentheses, the 1 plus x quantity to the 1/2 power. and we're able to simplify it, more so able to simplify it in the sense that we're able to get rid of that pesky square root, the power to the 1/2, and we're able to simplify it to what we're seeing here on this bottom line. And so we actually now have pretty much everything we need to be able to continue with our calculation that we started off with above, where we're looking at the change of velocities is equal to this d over delta t. And so now we're kind of back to what I was showing initially when I first transitioned to this page, with all the crazy math. We're not going to go through this line by line, but in so few words, you're able to go from the change in velocity on the first line, which is basically equal to the distance between the supernova and us, divided by the change in time that was associated with the detection of the particles that are the neutrinos I mentioned earlier. But basically, we're able to go to an equation where we can now look solely at what the rest mass of the neutrino would be, represented here by the m sub nu times c squared, which is actually the rest mass energy because of the fact that you have an m times c squared, but rest mass for the most part, or the rest mass energy, and how we can go about calculating that rest mass energy as a function of the total energies of the particles. Now note, the distance d we know from earlier, it was already given, or better yet, I found it somewhere online and basically just used the distance that I found online. Speed of light's a constant. The delta t we're getting from the plot that I showed, roughly about 12 seconds. And the energies, though, for the particles, we're also getting from the plot as well. So let me quickly take a quick moment to look at comments, because I've just been talking and talking and talking. All right, no comments so far. All right, so either that means that everyone understands everything I'm saying to this point, or I've completely lost everybody, and I hope it's not the latter. So yeah, whenever you're looking at these equations for particle interactions, C is always going to be there because typically it shows up in Einstein's formula for the energy mass equivalence. So C will, for the most part, always be there. And in fact, what really frustrates me whenever I'm looking at papers that talk about that have anything to do with particle physics, whether it's astroparticle physics or just particle physics papers, um, God, they all, for the most part, write C in natural units, or yeah, natural units, and basically they set C equal to 1. So C drops out of the equations, and it kind of throws me off because whenever I look at equations, I always also look at the units. And if a C is missing, it throws off the units in my head, and it makes me all confused. Now I have to backtrack to see where this unit should be, where the C should be located within the equation. But whenever I present these things, don't worry, guys. I'm not going to be dropping C's or anything like that. I'll try to make sure I keep up with them. But yeah, that's the primary reason why you'd probably see C. It shows up in equations for the mass energy equivalence relationship. So in this situation, we went ahead and we reduced it. Left hand side of the equation gives us the rest mass energy, and the right hand side of the equation gives us a way of being able to solve for a physical value for it. And that's kind of where I kind of left off at, was actually plugging and chugging in numbers to see exactly what the rest mass energy would be. Now, of course, I have not verified this. I haven't had time to verify it. But I kind of figured I would finish the problem, at the very least, and see what answer we get. And see if it's reasonable. Now, note, in our last discussion about the rest mass energy, if I'm remembering correctly, or at the very least, I know that if the rest mass of one of the species of of neutrinos is roughly somewhere around 50 MeV or greater. That's just one of them. Or if the sum of the rest mass of the neutrinos is equal to 50 eV or greater, then that would kind of coincide with the possibility of our universe being closed, having a closed geometry. And of course, in our discussion in last stream, a closed geometry would correspond to a fate of us undergoing a big crunch eventually in the future, many trillions of years in the future. So we have nothing to worry about. And even if mankind is still around to that at that moment, I mean, maybe we'll be advanced enough to be able to change our fate. Which I'm just playing about that. I mean, no, of course not. Um, but yeah. So let's go ahead and let's go ahead and figure out what these numbers are going to give us here. And thank you so much for the rockets. I just saw that. This illusion. Thank you. I always look at Pamela's streams and I love the rockets. Rockets are great. Oh, I'm sorry. I'm sorry. Don't underestimate us. I am not trying to underestimate anyone here. Not at all. Whenever I give these streams, I just don't want to run anyone away whenever I'm presenting math. But by all means, guys, like for example, if you guys see something wrong with my math here, tell me, because I make mistakes and it's happened in the past. All right. In fact, if I'm not mistaken, I see no yeah, no calculus today. No calculus today, Larry. Actually, in like my very first stream I did online, I did a calculation for well, not the very first stream, but I think it was like my third stream. I was doing a calculation that involved the escape velocity of Earth, and the calculation just completely. I made a really simple mistake, and I think it was Larry the one who caught it. It was like the I calculated the escape velocity of Earth, and Larry was like, "No, that's not the right escape velocity. That doesn't make sense." And I looked at it again. I was like, "He's right." Oh man, I made a mistake. But yeah, I make mistakes, guys. So if you see it, by all means, like let me know. All right. But yeah, by no means am I underestimating anyone. I don't want to run anyone away. That's all. Math is fun, and I just want to be able to share my love of it with you guys. All right. So these numbers, I'm not going to plug in the energy just yet because I'm running out of space on the right-hand side of the page. And you guys should be able to see that, yeah. So I'm just going to go ahead and solve what's in the over there with the numbers I've actually plugged in so far, which is basically just one big constant, right? Or information that was given. So back to this. So some quick math in my head here. Or better yet, nope, I'm not going to do that in my head. I'm going to do this. 2 times 1.6. So I'm using the calculator on my laptop here. So 2 times 1.6 times 9.5. And that is being divided by essentially 36. The 12 times 3 makes 36. And that gives me a nice number of 0.84. Okay. And then, of course, we can deal with the powers of 10. So this is your chance to kind of see me do math in real time. And this always scares me because I mean, I know I make mistakes, but I don't like making mistakes. All right, so as far as units are concerned, this should be unitless. Right. The units should break down to just being unitless for the numbers I'm calculating here. So I got a 0.84. Let's make sure I get this correct. I want to drop this out. So 0.84, and this is going to be times 10 raised to the So 5, 15, 20, 20 minus 8, 12. Right. So 10 raised to the 12th power. So a billion. And this is going to be unitless. So I'll typeset this so you guys can see the updated information. All right. Whoa. Now I'm very interested. I'm sorry, guys. As you guys probably already know, I can be easily distracted. And I'm seeing here that Larry's stating that the escape velocity, you learned it back in the 60s, but it was really important to Ranger missions. How so? While I continue with the problem, by all means, please tell me, because that sounds pretty interesting. All right. And so I'm going to go ahead now and plug in our energies. And so in this situation, whatever difference I calculate here, I want to use the absolute value of it. Oh, I see. I see. That is pretty cool. All right, so I want to be able to use the energies, and I honestly don't care if the answer comes out negative, because I'm going to use the absolute value anyway. Because of course the rest mass should be positive. All right, so excuse me. So I'm going to go ahead and modify this. So E1, you guys can't see me doing the modifications. Okay, all right, now I'm with you. So that's what you mean by Ranger missions here. I didn't know that actually. I'm not gonna lie. When you said Ranger missions, somewhere in my mind I was thinking military, and I'm like why would they need to know about the escape velocity back in the '60s? All right. So the energy, right? So one of the energies was at 9 MeV. So let's go ahead and keep this in units of EV. Right. So this is going to be 9, and this is 9 times. This is 10 raised to the 6th power. And guys, I apologize for not having these numbers already typed in because I know it takes time for me to type them. So EV, and that kind of slows things down a little bit. And the other one was 36. So 36 times 10 raised to the M, so 6 EV. So I typeset that. That information is plugged in. It's key that I go ahead and just do this now because it's all within that inner bracket is raised to the -1 power. And so I'm going to do this on my laptop. So 1, let's see. So 1 divided by that minus 1 divided by something else. And so this is going to be 9E6. So 9E6. So I'm actually plugging in the information into my computer here. So 36E6. That's a really small number. Okay. Oh wait, those are squared. Oh, that's fun. Okay, let's change this slightly. Okay. So I can do this. So I forgot to square those energies, and it's important that I do that. Otherwise, the math comes out all wrong. And so basically, inside the for the energies, I'm getting something like that's 1.16 times 10 to the negative 14 power. So let's go ahead and put that in. And I'm really hoping that this all comes out right, because like I said, I was in a mad rush and I didn't get the chance to actually verify. So, let's see, what was that? This fraction, all this fraction stuff can go away. Here. I can leave that. And I think the value I ended up getting was 1.16 roughly. So 1.16 times 10 raised to the negative 14 power. I'll typeset that. And this should be per EV squared. So it's important. I also want to keep track of the units too. There we go. All right. And so from here, I already know that my final answer is going to be in units of EV. I'm looking at this and I'm praying and hoping this comes out right, mathematically speaking. Unit-wise, it's coming out correctly, but the numbers are... I'm always afraid to get the wrong number because it looks weird at times. You get the wrong number. Let's see. All right, so we could do the reciprocal of that 1.16 times to the negative 14. So basically, it's the 0.84. Yeah, I could just do that. So 0.84 divided by 1.16. 0.84 divided by 1.16. That gives me a number of 0.72. Okay. So 0.72. Now, I have the 10 to the 12 over... Okay. I have 10 to the 12 over 10 to the negative 14. But the 10 to the negative 14 goes up top, so that's 10 to the 26 power. That seems insanely large. But we'll see. So times... This is going to be 10 to the 26 power. This is going to be with an EV squared, or EV raised to the negative, EV squared. And this is all within the parentheses. In a few seconds, I'm actually going to look at the number of people who are still here. I hope I haven't bored you guys to death so far with this. All right, so let's look at comments and everything else here. Yeah, neutrinos are extremely weird. And you know what? I've heard about the sterile neutrinos, but I don't know about their mass relative to the other neutrinos that have been around for much longer, or at least the ones we've been talking about much longer. All right, so I think initially the idea was that their mass was 0. But then eventually someone or researchers started to get that their mass was not 0. However, let's see, you said because I thought... But I think the consensus now is that they do have mass, but their mass is extremely small. Disillusion. Oh, I'm so sorry. I apologize. I'm always happy. I'm more than happy to be able to explain what I'm doing here. Basically, right now, I'm just I'm plugging these values into the calculator that's on my MacBook Pro here. Yeah, the letters are mostly gone. Um, on the left-hand side of the equation, those are still just variables. Where the m sub nu represents the in this case, you could think of it as like an average rest mass for the neutrino. The c squared is basically the speed of light squared. And this is equal to, and now what I've kind of changed here is that I've gotten it into units of EV, of electron volts. So I'm so sorry, guys. I'm like I said, if you guys have a question about a particular part of the calculation, or you want me to go back, I'm more than happy to do that. All right, so we've gotten to this square root, which I'm happy the square root's there because without it, the units don't work out properly. Yep, the 1/2 power can be resolved, exactly. It's very important that we resolve it, actually. However, I keep looking at this and I keep feeling like this is completely off. Yeah, this number I'm getting here is insanely large. But I'm going to continue, though. I'm going to continue. This is the reason why I like to get these things done ahead of time. I'm pretty sure somewhere in here, some either earlier on when I was dealing with the actual algebra, dealing with the variables, I did something probably goofy. But basically the final answer I'm going to get here, at the very least, the unit works out to just being in units of EV and not EV squared. But after applying that square root on the outside, that power of a 1/2, 0.72, and if I take the square root of that, is 0.84. But that's not the number I'm worried about. So 0.84. The number I'm worried about is 10 to the raised to the 26th power. So times the 10 to the 26th power, the square root of that is 10 to the 13. 10 to the 13, this is going to be units of EV, which I know is so wrong. And the reason why I know that this is so wrong is because if I put this in units of MEV, which is a common unit that's going to be used for these rest masses, either MEV or GeV, and I can put this in units of GeV as well, which is the reason why I know it's wrong. We're going to basically get what's this? M is 10 to the 6th power, 7. So we get 8.4. I think I'm doing this right. 8.4 times 10 raised 6, 7, carry the 1, 6. MEV. And this is so off. So somewhere in here, I've made a mistake. Oops, let's clear that up. And there. So unit-wise, I'm good. But that 8.4, so roughly a little bit above 8 million. 8 million MeV is insanely wrong. And I'm not too sure why. Where did I go wrong with this? I'm not too sure where I went wrong with it. I don't think it's the numbers. It would have to be somewhere earlier. Somewhere up here somewhere. But the time is now 1:18. But basically, this is the key thing I'm going to get at. In general, the approach that I've used can be used to calculate the neutrino rest mass. But somewhere with the algebra, not here, somewhere with the algebra I went wrong. And I'm not too sure where. It would take me a little bit of a moment to figure that out. But nevertheless, this was actually a very fun exercise for me. I hope that you guys were cool with it for the most part. And I would take the time to figure this out, but I have no idea how long that would take me. I would probably have to look at it for a little bit and see where exactly in the algebra I went wrong. Let's go back to comments here. So yeah, exactly. Wiki shows now these in particular so Wiki shows that the rest mass is less than or equal to 0.120 electron volts per c squared, right? And this was the 95% confidence level. And this is for the sum of 3 flavors. So in this situation, the value that they're showing here is for the sum of them, and not necessarily for any individual one. Give me soda. Yeah, I can definitely use the soda right now, actually. But I'm happy to know that it's interesting to you. Because it's interesting to me as well, even though I know I got the answer wrong here. It's still interesting, and I'm probably going to take a little bit of time afterwards, just for my own personal benefit, and figure out what happened with this calculation. I'm pretty sure it's the algebra mistake somewhere, but the overall process, I feel confident that you can kind of use to be able to get at the rest mass energy. At the very least, the unit came out correct, so I'm happy about that. Link to the PDF. Yeah, I'll actually, if you want, I can post this on the Weekly Space Hangout Cruise Slack. But let me do that now that you've actually asked for it. Let me first figure out the problem with the math here, fix it, and then I'll post it. I'll be more than happy to post it. If I made this discovery, so basically this is what this result's telling me. If the rest mass is equal to that, the universe is closed, and eventually at some point in time, it's going to collapse back onto itself. That's what that would be. That's what this result is basically indicating. I know that it should be a whole lot smaller than that. It should be less than 50 MeV. Oh, you want to fix it? You know what? By all means, I'll send it to you actually. And when you find out what's wrong with it, by all means, let me know where did I go wrong. Well, guys, the time is now 1:21 p.m. and I'm going to say that I had a great time having this discussion with you guys. I hope that you guys also had a good time as well. And so I look forward to seeing you guys on Friday. This time, I'm going to see if I can get started earlier. That is, if I present a problem, I'm going to get started early on it. That way, I can make sure I've gotten all the math kinks out. So just like Susie said, thanks guys for joining and watching, and having a great conversation about this topic. And I will see you guys on Friday after Daily Space. All right, guys. Bye.